session, we discuss about the quantum safe machine learning, securing AI in the post-quantum era. So here the quantum computing is an advanced concept. So with the quantum computing, we need to provide a more security, as well as we need to do a fast calculation and fast computings, and we need to solve the different kinds of threats with the help of quantum safe machine learning. So means in normal traditional machine learning, we may face some problems. How we solve those problems with a quantum safe machine learning? How we will provide the security in a security for a machine learning with the help of quantum computing. So before that, first we need to know about what is post quantum era. So coming to a post quantum era, so in a quantum computers, so maybe maybe we may face we may see this quantum computing in a seventh generation or sixth generation of computers. So this is a very advanced concept. So in a quantum computers, we can break classical cryptography like RSA, EC, and different Hamilton problems, algorithms. This means current security layers protecting. So ML pipelines in that it also protecting the data privacy, and AI models could be vulnerable. So we need quantum computers for what purpose? We need a quantum resistance method to reduce the to reduce or to secure the ML in a training, inference, and deployment. So in for give the security to the machine learning, we use a quantum computing. So coming to the next, so this is the agenda. Means these are the things we will discuss in the chat. So the first one is quantum. So in the fundamentals, we will learn about how to understand the quantum mechanics principles and their implications for a security. So how principles are going to be there, how it is used for a security, we will learn in the quantum computing fundamentals. So coming to threat landscape, here we will discuss all threats related to the quantum threats means attacks. So we will discuss all those things in a threat landscape. So how quantum computing challenges current ML security approaches, how it gives the tough competitions to a current ML security approaches. So that we will learn in a threat landscape. So next, quantum resistance algorithms. So in a quantum resistance algorithm, what type of algorithms, what type of models we are using, and what type of data we are using, what type of cryptographic techniques we are using to protect the ML models, that we will learn in a quantum resistance algorithms. So next, coming to implementation strategies. So how we will implement all these strategies and all these models to give the security to our machine learning, all we will learn in these implementation strategies. So the practical approaches to secure machine learning. So pipelines against quantum threats. So we learn these two things in implementation strategies. So coming to future proofing ML systems, long-term strategies, and industry roadmaps. So this is the last agenda of our session. So coming to the next first one, so fundamentals of quantum mechanics in a cryptography. So so here the main intention of a quantum computing or a quantum cryptography is to provide a security to the machine learning models, means ML models. That is the main motto or main intention of this quantum computing or quantum cryptography. So in the fundamentals, quantum mechanics introduces revolutionary principles that fundamentally transform how we approach security. So in these fundamentals, it will explain how we can approach for a better security. So here the first superposition, it means qubits exist in a multiple state simultaneously until observed. So here we will discuss about the uh, qubits. So these qubits are the main things. So everything will so everything is based on qubits only. Okay. So superposition, we will discuss about qubits existing in a multiple states. So actually, what is mean by a qubit? So qubit is the basic unit of information in a quantum computer. So it is the basic unit. So in classical computing, a bit can be either a 0 or 1. But in a quantum computing, a bit can be a 0, 1 or a, that superposition of both at the same time. Okay, so in a normal we use a zeros and one. Here we use a 0, 1 and a. That is superposition of both a comma, sorry, 0 and 1. Sometimes at the same time. So entanglement means paired qubits maintain instantaneous correlation regardless of a distance. So next, no cloning theorem. So quantum states cannot be perfectly copied without a detection. So next, quantum uncertainty. It measuring one property affects others, making eavesdropping detectable. So these four are the main fundamentals of the quantum mechanics. So by using these, we will calculate, we will do the computation parts for a security. Next, quantum key distribution, unbreakable communication. So how we can communicate in a quantum computing or a quantum cryptography. So here cryptography means we need to hide the data and we need to send the data in a secure way, in an encrypted way. So that is nothing but a cryptography. So for that, traditional cryptography, we may face some problems. They proper security with our traditional cryptography. So in RSA and so with the help of quantum, we can provide a more security. So QK leverages means quantum key distribution leverages next to keys that cannot be intercepted without a detection. So here we will generate different kinds of keys for a security purpose. So the BB84 protocol uses photons to establish a secure key between parties. So here we use a photon in our calculations. Based on that, we use we provide a security. So next, coming to the next, physical layer security, eavesdropping detection, future proof keys. So in a physical layer security, quantum key distribution provides security guaranteed by the laws of physics rather than a computational complexity. So based on a computational complexity, it gives the guarantee, it provides the security guarantee by the laws of physics. Next, eavesdropping detection. Any attempt to measure quantum states disturbs them, immediately alerting legitimate users. So if is there any disturbance happens, so it quickly alerts to users. Then we can detect easily. So future proof keys, keys generated through QKD means quantum key distribution remain secure even against future quantum computers. So with the help of these keys, I already told we will provide a security. So it is like a private key or like a private key. So quantum computing based quantum. So this is a computing and this is a quantum computing. So this is just a comparison of classical computing and previously how we will compute quantum computing, how we are computing computers. So bit exists in definite states 0 or 1. So here qubits exist in a superposition, that is 0, 1 and a superposition at the same time. Operators are deterministics. Here the operations leverage probability amplitudes. Here we use some probability for a computing. So limited to sequential processing. So exploits quantum parallelism in quantum computing. So here the complex problems require exponential time. so can solve problems exponentially fast. So in classical computing, so sometimes there may be a problem to solve complex problems. So even if we solve it, takes much time. So in quantum computing, we can solve in easy way and quick way. This fundamental shift in computing paradigm creates both unprecedented opportunities and security challenges for ML systems. So it provides some opportunities and security challenges for ML systems. Next, quantum building blocks. Quantum building blocks. Here we can see gates and circuits. How we can implement these logic gates and circuits in a quantum computing in computers. So quantum gates. So here, unlike classical gates, we use and or not. Quantum gates are reversible transformations represented by unitary matrices. So here we use and or not gates in a classical gates. For a uh, quantum gates are reversible for a transformation purpose. We use these gates. So here, Hadamard gate H creates a superposition. It creates a superposition means qubits. So poly gates XYZ bit flips and phase shifts. It provides the flips and phase shifts. C naught gate entangles qubits. So it provides the it explains about the qubits. The last gate is coming to quantum circuits. Above are the quantum gates we use in quantum computing. So in quantum computing, we use the quantum circuits, sequence of quantum gates applied to qubits to perform algorithms. So here we will perform all algorithms. For that, we combined all the gates and we apply to the qubits for performing an algorithms. So initialize the qubits to state. Here we will apply gates in sequence manner. Then we will measure the final state of a classical output. May require multiple for a probabilistic results. So sometimes it may require multiple runs for get a for a probabilistic results. So we can get the classical output in easy way, but we cannot get the probabilistic output in an easy way. So these are the some quantum algorithms we use in quantum computing. So the first one is Gruber's algorithm. So Shor's algorithm we use and quantum simulation we use. So coming to the Gruber's algorithm, so quadratic speed up for unstructured search problems. For search problem, we use this Gruber's algorithm. By this we can speed up our search in a quantum computing. So reduces complexity from O of n to O of under root n. So means it reduces the complexity problems in a better way. So impact weakness symmetric cryptography. So impact here, the weakness is the weakness symmetric cryptography here. So example, AES algorithm. So by reducing a key strength, so it will reduces the key strength. Coming to Shor's algorithm, so in exponential speed up for integration factorization. So here also uh, we will exponential the speed up for integration factorization. It reduces the complexity from sub-exponential to polynomial time. So it also reduces the complexity in a quantum computing. So if we are reducing the complexity, we can easily do all the things in a quantum computing.